Hello everyone, I'm Cole from my channel. Today we're going to discuss two different factors affecting intensity of X-ray diffraction. The first one is in polarization factors influenced by the one electrons. And the other one is Lorentz factors associated with real X-ray diffraction testing. The first factor we need to study is polarization factors. This influenced by one electrons polarization factors. For the calculation of polarization and Lorentz factors, and then we need to consider physical equation that seems to be very complicated. Then, so I want to show you some final result because the intensity is simply not equal to the final equation, just kind of showing some proportional behavior with some final equation we derived today. One electron, let's say electron, we just give a white X-ray as a electromagnetic wave, and after that there's some kind of diffraction, and then we can give some specific definition to this angle as a 2 theta. Intensity cannot be measured right after the electron. It's impossible. So there's some kind of certain points away from the one electron. Let's say this is the P. P position we can find X-ray detector. So that's why intensity should be coming from P position. So the equation intensity at the position of P will be 1 plus cosine square 2 theta over 2, this value. Yeah, it's all finished. Second is polarization factor. After polarization factors, we need to consider Lorentz factor. The Lorentz factor, there are two different things, and actually there's three, but we can make a grouping. And then the first one, from the Bragg peak. Bragg peak means, and then y-axis intensity, x-axis 2 theta value. So there must be something we need to consider. The second thing associated Lorentz factor is 3D X-ray testing, XRD testing. This one divided into two different things. The first one is I just give some keyword, the little difference. The other one is 3D cone. I will explain very soon. The first of all, we start with from Bragg and what kind of Lorentz factor we need to consider. I will just provide representative specific peak of some sample after diffraction testing. Y-axis is intensity arbitrary unit, x-axis 2 theta value, right? And then the diffraction angle can be calculated and then a fixed one, let's say in 20.4 degree. So what about our peak? Very thin this way? No. The real experiment, we can see some broad peak like this, right? So in this case, and then we need to consider these all areas, integrated area beneath this curve. We need to consider that. Why? This angle, 자, this angle, the lower than 20.4, also some angle higher than 24, also contribute this specific intensity of this peak, right? So how can we calculate, let's say, this maximum value? This value will be I maximum, max. And then I want to give you very, very important nomenclature. And then 자, F, W, H, M. It's very important. This one is full width. Where? At half a maximum. The which point and then half maximum, this value, half, just find this value, and then we measure this width. So this blue area can be defined full maximum, full width, and half maximum, FWHM. This is a very kind of the measurements that describe the width of the distribution and the peak at the half of its minimum value. So please remember this one. Simply here we just say W value. So we just integrate this area, yellow area. So I integral. And just roughly, 자, I maximum value mx, max, and multiply by w. FWHM, full width and half maximum. So there must be physical calculation. I'll just show you final result. I maximum is inversely proportional of the sine theta. So 1 over sine theta, and the width also 1 over cosine theta. We know sine theta, cosine theta. So final result is should be sine 2 theta, right? Professor, where is the 2? I just give a number, give us some equation like this proportional symbol instead of equal. This is the point. So this all finish, and then we move on the three-dimensional X-ray testing. 자, 2.2 right here, and three-dimensional XRD. Our results is just two-dimensional space, but real X-ray diffraction is a three-dimensional one. So we can provide some specific sphere structure. And these spheres defines diffractor, meter, circle. This means, and then certain points, and then our X-ray detector will be located. And then where is our sample? Our sample here, and then X-ray peak, X-ray some light, and then it show some kind of diffraction three-dimensionally in this way. This is the real situation. So first of all, we must know, and then the two different things, and then we just magnify this area. That area, we just magnify. we're going to use powders of a certain material. So one powder, the other powder, there are many powder. It's really polycrystalline, and then this means each powder they have their own orientation. 자, I just give you some specific orientation. This one. But if you take a look at here, and this one, the orientation seems to be quite similar each other, right? This orientation, angle between them is almost negligible. This means actually we need this one, but this also can be diffracted, right? This is talking about little difference from its orientation when we just going to use powder material, right? Also, we consider another things, and then from this one, and then after diffraction, we simply only two-dimensional space and then only this one. But the real experiment happen in the three-dimensional space. So diffraction will be made along with this kind of circle, right? So we need to consider this cone structure. Cone. So 3D cone here. So equation will be I integral simplify cosine theta and sine the 2 theta value. 자, cosine theta value is from the polycrystalline itself, and then cone also associated with sine 2 theta. So here and there you only remember three different angle relationship. The first one from the polarization factors and intensity at the position of P away from the electron, 1 plus cosine square 2 theta over 2. And then as a Lorentz factor, there are three different. But from the concept itself, it should be 2. The first one, and then little difference from the powder metallurgy as a polycrystalline material, and also together with consideration of three-dimensional cone within diffractometer circle, and then integral this one, and before that, and also from the Bragg curve, we also consider 1 over sine 2 theta value, polarization factor and Lorentz factor. They are function of theta. Okay, here we need to check it out. The previous one, structure factor, is function of h, k, l together with fractional coordinates. Not a shape, not a length of the specific one, right? You have to remember this one. So different from the structure factor, the previous one, today's lectures and polarization Lorentz factor is function of the theta. That's how we can combine all together. So P, L, F. The initial, some textbook use L-PF. There are many things, but at least you know polarization Lorentz factor can be combined 1. 자, the result is, and then we just draw polarization factors. The function of theta angle cosine 2 theta over 2, right? So we just give this value, but the here, and then we just eliminate neglect and then 2. So 1 plus cosine square 2 theta, right? And then we need to consider Lorentz factor. 자, Lorentz factors. 자, here. 자, sine 2 theta. The first one, and then cosine theta. Last one, once again, sine 2 theta. 자, sine 2 theta will be 2 sine theta cosine theta. cosine theta again. 자, 2 sine theta cosine theta. 자, cosine theta is same. The result is 4 sine theta square cosine theta, right? This also 4. It's a certain value, so also we just ignore this 4. So we just give sine 2 theta square cosine theta. This one. So the final result is simply combine all. 1 plus cosine 2 theta square sine theta square cosine theta. That's one mistake, not sine 2 theta, and then so this final equation will be just like this. Once again, polarization factor and Lorentz factor can be combined into one because they are function of theta Bragg angle. And then we can formulate, and then this tendency with respect to the theta angle, and then you must know some kind of tendency. This one, polarization Lorentz factor, the intensity value, and x-axis, and 2 theta. The rough curve will be just like this, and then it's very high curve and decrease and showing the local minimum, and then increase again. So normally, and then from the calculation, that angle is 100 approximately, and then it has very small value, 2.7. So that's why the lowest value of the polarization Lorentz factor will be achieved approximately 100 degree, and high value, fairly high value near to 0 or 180, and then showing the high the value. And then today's lecture can be summarized into two different categories. The first one, electron-induced polarization factors, that is function of theta Bragg angle. The other one is also another important things from the real X-ray diffraction testing, that is Lorentz factor. Yeah, surely it's also function of theta that can be combined into one equation. So next time we need to prepare two more factors. First one is multiplicity factors associated with crystal structures. The other one is last one, and then temperature factor.